Good afternoon, everyone. So, in this lecture, I'm going to primarily talk about some brief introduction about food processing. So, I think a class like this normally have people with different backgrounds, and some probably take engineering classes, some take microbiology, some come from traditional um, chemistry or other fields. So, because food science and engineering attracts people with a diverse background, so that's where I think introduction is always helpful. And food science and technology is a multidisciplinary field. So that means you need to know the engineering, you need to know the chemistry, you need to know the microbiology. You also probably need to know the various other things, like for example, some aspects of business if you are working in the industry, because you are making product, but if you are not selling them, if you are not selling them in an economical way, it's not going to be viable, commercially viable. So you have to kind of familiar with that. So today, I think we also look at, when you look at some of the processing technologies, in addition to some of these fields, you have to look at the nutrition and health, because traditionally food processing is validated based on microbiological safety, but more and more the consumers are interested in health and wellness. So there is an interest to see how much nutrients are preserved by different technologies, so you can able to choose the one which preserve the nutrients better compared to the other one. Now, if you look at the consumers, they normally very much interested in sustainability. At least a lot of statements I make is based on the US consumers, but that may be true for Indian consumers as well, but we can discuss that during the discussion session later on. But when I look at sustainability, a lot of consumers want sustainable product, but when you ask how much they're willing to pay, are they willing to pay additional premium for the sustainable effort, usually they do not want to do that. So they still want to have economical, affordable product. So it's kind of, they expect the food processor to take care of the sustainable effort, but nevertheless, they want something affordable. Consumer acceptance is also very important when you look at the some of these technologies. Again, in the US, if you look at food radiation, it has been mentioned many times that it is scientifically very safe and commercially viable technology. However, today, this is something have been proven in the 1950s and 60s, but even today the radiation is not commercially available. Part of the reason is that consumers associate with radiation with the nuclear war, and they kind of worried consuming some radioactive product, even though scientifically shown the food are not radioactive, like after treating with radiation. So consumer acceptance is very important. The supply chain is also very important, because especially when you are processing new technology products, the vendor may not have the proper supply chain, so that affect. And we have seen the supply chain effects during COVID, because with the COVID, a lot of the supply chain and manufacturing, everything is get upset, and as a result, I think a lot of changes probably happen. So when you develop a technology, just because you are an engineer, you have a very good idea, do not expect that to be commercially successful. You need to be able to make sure your broader knowledge is important, so that you can be able to make it a viable technology. If you follow social media and then also food processing, you probably hear a lot of things, particularly about food processing. People say food processing is bad. I think processed food, ultra processed food is evil, and all those type of things. While there may be an element of truth to it, but I think the ordinary consumer probably do not understand what causing the processed food become unhealthy. So if you look at processed food, you have two things. One is processing. That means it can go through a heat treatment, it can go through a pressure treatment, electric field treatment. So it's a process side. The second thing is formulation or product development. So when you product develop, you may be adding a lot of synthetic ingredients, and some of those ingredients probably cause the adverse effect, especially some of these ingredients may not be properly tested, and if that ingredients are not properly tested, so they may provide certain functionality, for example adding certain flavor, but it may have some side effect on your gut microflora, and that's where the people get sick and feeling and so on. But a lay consumer probably do not understand what is the difference between adding ingredients versus processing, and they think that summarily reject processing as the evil for all those things. Now, I think later part of this class, we will also talk about some of the new processing technologies. So when you look at thermal processing, while it is traditionally make the food safe, it also degrade quality, it also degrade flavor and many other product attributes. So I think the newer processing technologies have minimal processing technologies. In other words, they minimize the thermal exposure, they can able to preserve the quality attributes while making the food safe. So we'll kind of talk about some of those things. But other than that, I think food processing has numerous benefits, including increase in diversity, safety, convenience, flavor, texture, like I think fortification enrichment, like for example, when you look at rice, you can probably fortify rice with number of nutrients so that it may not be otherwise possible. You have milk, you may be fortified with certain vitamins so that it can kind of provide certain benefits and so on. And so I think overall, processing technology has a number of benefits, but as a food science and engineering community, we have done poor job in communicating the benefits of food processing. So that's where you have a lot of the negative commentary comes in. And if you look at it one way, all of us are living in the globe, we are all consumers, and we consume at least 3 meals a day, most of us. And so that means the food science and engineering contributions there to take that raw product, convert them into value added product and bring them to the table. So I think in that sense, food engineers, food scientists play a key role in terms of creating that value added processing. But if you ask a lay consumer, they may not know who is food engineer is or who is a food scientist is. They primarily know farmer, or they may know the end side, but they may not know somewhere in between. There's a scientific communities there. So that's something, as some of you get into the academic and you may want to communicate to the public the importance of some of these processing methods. Now, I think the next couple of slides, I'm going to try to quickly go through some basic concepts. So if you already have these basic concepts, it's a review, or you may be sitting here and teaching this, or some of you probably new, so you may kind of learn. One of the key thing is mass balance, because in food processing, you are taking raw product and then convert them into value-added product. A simple example is, like for example, you take some orange fruit, you kind of remove the peel, and then you extract the juice, and then you have the final product. And if you look at the mass, you still have that mass balance probably going to come in. So you have, say, 1,000 kilograms of orange fruit is there, and then maybe 60% of fruit is peeled, and skin and everything, and then maybe you have 30-40% of juice comes out. So that's a simple mass balance. This mass balance help you to understand what is going inside your processing equipment, what's coming out, what is wasted, and the idea here is, how do I reuse some of this waste so that I can minimize the waste, because in the past, wastage in food processing is not something big concern, whereas now I think there's more and more efforts on valorization. I think they want to, how do you minimize the waste by getting some of the ingredients. So for example, if you are processing some tomato juice, you extract the juice and you throw away the pomace, but the tomato skin, the pulp, the pomace has a lot of what they call nutrients in there, and those lycopene and other ingredients may be extracted from the skin that can provide a value added type product. So having a sense of mass balance always help you to understand, and whether you do in a small lab scale with a 5 gram, 10 gram of sample, or you do it in a 1 ton type of industrial sample, mass balance always helpful to have. Energy balance, again, with today's interest in sustainability, the goal is to minimize the energy use, but food processing use variety of energy sources. Traditionally, a lot of the foods are heat processed, so you may be doing blanching, you may be doing pasteurization, you may be doing commercial sterilization, or some of the new processing methods using high pressure or radiation. So these are all different forms of energy sources, and part of those energy is going to modify the food, kill the bacteria, and you kind of make the food palatable. So when you pasteurize or sterilize, the same thing happens when you do radiation or high pressure processing or pulse electric field processing. So again, here you have to look at how much energy you input, how much energy you gain, or what's the output, and then how much energy is wasted and so on. And you have to kind of find a way to reduce some of those energy use. So traditional sense, you probably employ a lot of pumps, heat exchangers, and many of the devices to process food. So you can probably find a way to better utilize the heat exchangers, so you can have much more efficient heat exchanging systems. You can use a better pumping efficiency so that you can reduce the energy use in some of those things. When you are using microwave or warm heating, you are using electrical energy. If you look at traditional thermal processing, you take steam and convert that steam to heat your pasteurization equipment or canning equipment. So steam is produced off-site and then transported to the processing plant. Along the way, there's a lot of energy is kind of wasted, and that's kind of oftentimes ignored. Now, on the other hand, when you have microwave or warm heating, you produce electricity, and that electricity is converted into microwave or warm heating that directly impinge on your surface and then convert into electrical energy to treat the food. So it's much more energy efficient. The same way, some of the new processing technologies like high pressure processing or pulse electric field processing use electrical systems, so they probably make things much more energy efficient. Another consideration is that when you have electrical energy systems, you can kind of take that and use many ways of producing electricity. So for example, in India we have abundance of solar power, so you can produce electricity using solar and then use one of these technologies to do processing rather than creating steam, which can have harmful emissions and things of that nature. So that's kind of, again, the energy balance is something important. Now this slide just to show when you do food processing, you're probably going to have both mass balance and energy balance needs to be coupled, and they need to be considered. So for example, you may be taking some tomato puree and maybe adding some water, mixing it, and then maybe create some type of juice type of product. You may have certain water need, energy, and then you probably have certain output. So you have to consider along the way what you input, what you are outputting, and what's wasted, and all those things. And so you always kind of pay attention to reduce the energy use and reduce the water use. Now, most of the foods processed today, these are heat processed or thermally processed. Even though there's a lot of excitement about novel processing technologies, these technologies are still at infancy. So that means maybe 5 or 10% of the products are processed with the new technologies, maybe more in the future, but today most of the foods are thermally processed. So still we need to understand the thermal processing basics so that we can able to understand them. So one of the bigger way the heat is transferred within the food is through 3 sources of heating: conduction, convection, and radiation. So conduction heat transfer is the heat transfer taking in solids. So here you have molecules within the solids. They kind of agitate and then transfer heat from one molecule to other molecule. Convection heat transfer, essentially the heat transfer taking place in liquids, like for example when you are boiling water, the heat transfer taking place is convection heat transfer. Radiation is the heat transfer taking in free space. When you are walking on a hot day today, like today, you can see, you feel warmth from the sun. Even though sun is away so many miles away, you still feel the heat because the heat is transferred through radiation. So in terms of conduction heat transfer, the example is, if you have a piece of potato, you are heating the potato, the heat transfer taking place within the potato is an example for conduction. So that means you have transferring heat from the outside of the potato. Let's say the potato you put in a boiling water, the water is at 100 Celsius, the potato is at 25 degrees Celsius. So when you drop it in the boiling water, initially it may be 25 Celsius, and then slowly the surface start warm to higher temperature, and then eventually reach 100 Celsius. Then the heat is diffusing through the interior of the product, and then eventually the whole thing is going to reach 100 Celsius. So conduction heat transfer is size dependent. So that means if you have a small product like pea, you can able to heat it quickly, whereas if you have a massive say some meat product or chicken, then that takes longer time to cook because the heat transfer is very long. So if you look at some of the newer processing methods like microwave or warm heating, that conduction heat transfer limitation can be overcome because microwave can heat the entire mass of the product in a single operation, so that you can able to heat the whole thing and you can minimize that temperature gradient. Because whenever there is a temperature gradient in the product, that means maybe portion of the product which already reached, it may be degrading, whereas the portion of the product still reaching the temperature may not be cooked if properly. That can be a food safety problem. So understanding the conduction, convection, and radiation heat transfer is one of the very critical thing when you are doing food safety assessment, as well as probably looking at the nutrition assessment. Again, I'm just going through basics, but probably you may want to refresh if you are not familiar with some of the concepts. So heat exchangers, these are devices where you can exchange heat from say hot steam to maybe your product which is at a different temperature. And heat exchanger can mean different things. So, for example, if you have an evaporator, you may be concentrating liquids. On the other hand, if you have a freezer, you are going to cool it down. That itself is a heat exchanger, and so that you can extend the shelf life by freezing. You have pasteurization, sterilization, ovens, fryers, microwave heaters. So there is all different type of heat exchanger equipments are available. Now, when you are doing food processing, we are going to consider, assuming a lot of things are heat processed, there are a couple of things going to happen. One, there is something called reaction kinetics is going to take place. The second is something called transport phenomena, and then the impact of process. So, what is reaction kinetics? So, when you look at the raw product, you have a potato, you have a meat product that contains maybe a lot of nutrients, it also have a lot of microorganisms. Our goal for food processing is by heating that potato, you kill any harmful bacteria and any spoilage bacteria, while you want to retain as much as nutrient as possible without destroying. Now, chances are some nutrients are heat sensitive. So, when you are heat treating, some of those nutrients may be damaged while you are killing some of the other products. So, this is where you are going to look at the reaction kinetics you have to consider. You have to consider the microorganisms, the quality attributes, because when you are heating that potato, the potato initially very firm, then as it gains more heat, it's cooked, it has starch conversions, all those things taking place, it becoming more and more mushy. And if you look at a canned potato, it looks much more mushy because they want to ensure it's fully cooked so that all the microorganisms are dead. But it also compromises the nutrition and the textural attributes. So, this is where you have to look at the microbiological safety. The second part of it is the transport phenomena, and during cooking or heat treatment, you have to look at the heat transfer. So, for example, you have a can of peas or meat or whatever it is you are cooking, you have to see how uniformly heat is applied in your treatment. In addition to that, you also look at how uniformly heat applied inside that big vessel where it's maybe canning equipment, retard, or pasteurizer, or microwave sterilizer, and so on. So, how uniformly temperatures are distributed. So, the treatment uniformity is very important, because a lot of the kinetic models assume your microorganisms are killed at a particular temperature for particular time. So, when you are doing an industrial scale, it's almost impossible to maintain that uniformity, but you want to develop approaches that maintain that uniformity as much as possible. You may also have mass transfer taking place. So, for example, when you are frying potato, the potato is going to absorb fat from the oil. It may give up water from the tissue. So, this can be mass transfer taking place. So, you need to understand the mass transfer as well. And then you also need to pay attention to the what they call engineering properties. A lot of times when we ask what is the engineering properties, sometimes students may erroneously tell it's the color, or it may be the water activity, texture, those type of things. Those are all product attributes, but not necessarily the engineering properties I am mentioning. The engineering properties I mentioned here are the thermal conductivity, the specific heat, the density, some of those things. We will talk more about those things. These again control how uniformly the food is heated or the process is delivered, so that you can able to get that thing done. So, once you establish the microbiological safety, uniformity of the process, you can establish a whole wholesome uniform process. So, here we kind of kind of went through this here, and I think this is a picture of an autoclave, just to give an example how an autoclave may look like. If I have a person standing here, the person may look very minuscule because this is much larger diameter and much larger in length, and then he may be putting several tons of product depending on the size of the retort and other things. And this slide here just to show that how your for example, the temperature distribution during microwave heating or other process being verified either by mathematical modeling or through experimental measurements. So these are some of the key engineering properties I talked about. Thermal conductivity is the ability of the material to conduct heat. So when you look at metals like steel or things like that, they can conduct heat much more quickly. When you look at the insulation materials like plastics, they conduct heat very slowly. On the other hand, if you look at food materials, they were intermediately conduct heat. So that's something we need to know. Specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. So how much energy you need to raise the temperature by heating. Density, the compactness, it's basically mass per unit volume. Thermal diffusivity, basically you take the thermal conductivity, specific heat, density, and then you kind of divide K by rho Cp. So it's kind of the unit, so how uniformly the heat is distributed during processing. You may have some liquid fluids. The viscosity can provide an idea the resistance of a fluid to deformation during flow. So when you want to pump different fluids, you can able to get this. And again, there's a whole set of field called rheology, Newtonian, non-Newtonian fluids, which I'm not going to go over here, but you need to understand so that you can able to get some of these things covered properly. When you look at some of the newer technologies, the compressibility is another parameter you look at. Like we talk about high pressure processing. High pressure processing, you are applying 600 megapascal pressure to pasteurized food. So normally when you have 1 liter volume of water, during processing it's reduced by 15%. So in other words, it's going to go from 1 liter to 0.85 liters. So there's a 15% reduction in volume taking place, and that's the compressibility. So different substances, fats, lipids, protein, different compressibility values. When you look at the electrical technologies like microwave heating or ohmic heating, the electrical conductivity property is important. So similar to thermal conductivity, it's the ability of the material to conduct electricity that's important. When you look at freezing type technologies, you need to understand the latent heat. So the latent heat, basically how much energy you need to provide or extract to require a phase change. So for example, you have water convert into ice. So that means you are going to remove certain latent heat. Or you have ice, you are adding certain heat, it converts into water. So again, you are going to add certain latent heat. So what's the difference between sensible heat and latent heat? So there's two forms of heat. Sensible heat is something you can able to measure temperature change by monitoring using a thermocouple. So for example, when you take a beaker of water and then you put it in the thermometer and then you heat the water, you can see the thermometer going to show the temperature increase from 25, 50, 75 Celsius and so on. So you can see the phase change. On the other hand, you take the same beaker and then you heat until everything converts into water. When the water reaches close to 100 Celsius, the thermometer is going to stop showing any temperature change even though heat is continuously applied. Then a lot of those energy goes into converting the phase from liquid into vapor, so that way you're going to show that as a latent heat. On the other side, when you're freezing it, that heat energy is going to convert that into ice. So again, you have to kind of consider that form of energy. Now, some of these things are engineering properties, but there are certain chemical properties also important. One is the product acidity. The acidity is very important. A lot of the foods are neutral pH, whereas you probably have certain fruits and other things are acidic. And why acidity is important? Because microorganisms, like living beings, they also do not like very acidic environment. So that means if you have a pH of less than 4.6, that generally inhibit the growth of microorganisms, whereas when the pH is above 4.6 or more close to 6 or 7, the microorganisms like it and they can thrive well. So that means your processing treatment may be different. The severity of the treatment may be needed when you have pH is close to 6 or 7, whereas the pH is less than 4.6, you can have less severe treatment is sufficient. So that's why pH is important. So when you are processing any food, you always try to understand, measure pH and water activity, because that will probably help to decide what type of treatment you need. Similarly, water activity. The water activity basically going to tell you, how much water available for certain microbial reactions or chemical reactions. And again, 0.85 was above 0.85, like raw food materials, they probably permit growth of microorganisms. Whereas when the water activity is less than 0.85, say 0.7, 0.6, you have less water available for chemical reactions or microbial reactions. And when the reaction water activity value is about 0.2, 0.1, then even more better. So that's where again you have to consider microorganisms and water activity and how they interact with pH, all those things. Normally, in the US regulations, they classify foods as a low acid food and high acid foods. So low acid means it has a low acidic content, so that means the pH is above 4.6. And then the water activity is 0.85. So many vegetables, meat products, dairy products, and it allows the growth of the Clostridium botulinum. So I mentioned pH of 4.6. What is the magic about 4.6? And I mentioned here Clostridium botulinum. So Clostridium botulinum is probably one of the deadliest spore-forming bacteria. It has an effect on human brain and other things. So they can form toxin and they can cause death. So they require above 4.6 to survive and proliferate, whereas less than 4.6 they are inhibited. So that's why it's called low acid food. High acid foods, like for example, you may have juice and other products, they have pH less than 4.6, and here you can have a mild treatment. So just to give an idea, if you have a soup, generally potato soup, it's more neutral pH. You may have to, if you need to do the canning, you have to treat that maybe 121 Celsius for a longer time. Whereas if you have a tomato juice, generally the pH is less than 4.6, then acidic, you don't need to go all the way to 121 Celsius, probably somewhere 90 Celsius or 100 Celsius for a few minutes is sufficient because it's more acidic product. So the acidity determines how intensive or less intensive the heat treatment can be. Acidified products, basically you have a low acid product, you can just add in the formulation some acid. So for example, you may have pickle, the vegetables, you can add some acid to it or things like that, so that the product become acidified Once it's acidified, you can treat them like a high acid product, thereby you can have a less treatment and longer shelf life. Some engineers, if you are a particularly chemical engineering or other disciplines, you may not familiar with the microbiology, because I think you may not have those coursework part of your curriculum. So a brief introduction for microbiology is kind of given here. So if you look at the very small 0.1 nanometer is probably you deal with atom, whereas if you have 10 to 100 microns, you probably have viruses, flu virus and things like that. Bacteria is probably somewhere 1 to 10 micrometers, and then plant cells are much larger compared to the microorganisms. So this is kind of gives you some idea the relative size of different microorganisms. That's something we have to deal with. So what that means is, if you are going to kill the bacteria, your viruses and things like that, you are also going to destroy your plant cells and animal cells. So anytime you are going to destroy with the purpose of killing the bacteria and things like that, you are going to affect your plant cells, animal cells. That means you are going to degrade the product quality. So the challenge is, of course, how do I minimize that degradation? How do I keep my plant cells, animal cells, so that it's more intact, so that I have much more wholesome, nutritious product? So that's a challenge, as a food process engineer you deal with. Now, in terms of microorganisms, there are classifications. Psychrophiles, these are microorganisms. Basically, they love refrigeration conditions. They can grow well in 1 to 20 Celsius. Psychrotropic conditions, these are grow at 37 Celsius, for example, Listeria monocytogenes. Mesophiles, they can grow 20 to 40 Celsius, and then thermophiles are heat resistant, so Bacillus thermophilus. So again, we had to kind of understand some of these microorganisms, what is the best growth conditions, all those things, because when you are processing food, you need to understand, depending on where do you store, what temperature you are storing, you have to make sure these microorganisms or get rid of them part of your study. Now, you may hear the term pasteurization, and you may hear the term commercial sterilization. We will define that in a later slide, but here what we are trying to highlight is what happens when you do pasteurize or commercially sterilize, what type of organisms you are going to get rid of. You can see that when you do pasteurization, you are going to get rid of cells from the psychotropes, mesophiles, thermophiles, and maybe some of them still survive, but spores kind of survive the treatment during pasteurization. So that means you have to store the refrigerated product, pasteurized product in the refrigerators, because otherwise spores can outgrow and cause an outbreak. On the other hand, commercial sterilization, which is much more severe form of treatment, you can probably able to get rid of all the different forms of organisms. So this is something you have to pay. And then ESL is basically extended shelf life. So this is kind of an intermediate type processing. It's more severe than pasteurization, but less severe than commercial sterilization. So here in summary, pasteurization is a mild treatment, so that you can get rid of the vegetative form of bacteria. Spores survive, require refrigeration storage. The shelf life may be shorter, maybe a couple of weeks, maybe a month. Whereas commercial sterilization is a severe treatment. You get rid of both severe bacterial spore as well as vegetative form of bacteria. The product can be ambient stable and have a longer shelf life, maybe 1 year to 1 to 3 years and so on. Now I'm going to transition from traditional conventional technology to new processing technology. And if you look at here, and the history of food processing is going to be helpful. It's not that we humans in the modern era first invented cooking, canning, all some of these things. People have been doing this thousands of years. So before 1900s, people doing cooking, drying, salting, pickling, all kind of stuff over many thousands of years. Only in the 1900s, the industrial food manufacturing began to emerge, and in the US, this also led to Food and Drug Cosmetic Act (FTC) Act kind of came in, which started regulating food industry. So 1906 is kind of give an idea. So 1900, pasteurization, commercial sterilization, these are all considered at the time new technologies. So a lot of the regulations, a lot of the experimentation on pasteurization, sterilization happened. And in the 1940s to 60s, the pasteurization, sterilization became more standards. Then they also introduced a lot of the freezing, refrigeration, those type of things became more common. And then people started experimenting microwaves and so on. And the 60s and 90s led to the development of advanced thermal processing technologies like microwave heating, radio frequency heating, ohmic heating, all those technologies kind of becoming more and more looked at. 80s to 2010, I think if you look at here, the focus kind of, if you look at the earlier years, the focus is primarily food safety and quality, but not much concern about nutrition. Then in the 80s to 2010, the nutrition become more important. So this is where the non-thermal technologies begin to emerge, where you can use like a high pressure pulse electric field. So you also not only make the food safe, but also preserve the nutrients. Fast forward 2010 to 2025, you have more and more concern start emerge about the health and wellness, also the sustainability. So that means there's a demand for clean label products. So basically people said, I don't want any more synthetic ingredients in my label statements. I want more natural ingredients in my product label, and then also want sustainable. Now this is where India may be different from Western society. We have been using plant proteins thousands of years, whereas the Western society just to begin to understand the importance of soybean and many other plant proteins. So now they call this as alternative proteins. So they start using alternative proteins to formulate some of the meat-like products and so on, so forth, from a sustainability benefits point of view. Because we will talk later on in sustainability, to grow some animals like cow or anything, it takes several thousand subliters of water, and so to create some 1 pound of meat, it takes a lot of water. On the other hand, if you use a plant protein, you can probably use much less water. So the idea here is, if you need to consume meat for growing population, it's much more difficult to do that, whereas plant protein is much more economical way of doing that. So that's basically there. And then in the future, you're probably going to some of these trends continue, and then you may also have introduction of automation, AI, artificial intelligence, many of those things get into the food processing industry. So in other words, the food processing industry never been a dull, it's a dynamic, it's always innovative. It's also constantly change with the consumer demand. It's that maybe one company may not change, but the rest of the companies or new players emerge to satisfy the consumer demand for innovations. Now, what are the challenges in food processing? Like by 2050, there's going to be significant growth in the world population. So, and we also see globally there's a significant increase in the middle class. It used to be a lot of affluency is in the Western countries, and the developing countries like India, China, and others, probably in the 70s and 80s, they were not that affluent. Whereas today, the affluency is kind of spread around the globe. So that means all the people probably want more healthy food, nutritious food. So how do I feed growing population safe and nutritious food? So that's something we need. And People also said no artificial ingredients, preservatives, convenient taste, and they want to also reduce the environmental impact and sustainability. So this is from a consumer perspective. Food processor, they are there doing, it's a business for them. They are not necessarily going to freely give away samples for people. So they want technologies which can do things faster, better, cheaper, and then has a breadth of application. So in other words, they don't want a technology which probably just pasteurize milk. That's the only thing it does. They don't want that. They want maybe 10 different things that technology can help them to do. And they also want to make sure that the technology is accepted by consumers and then it's accepted by regulators. The regulators, whether it's in India or US, you have regulations coming from international, you have federal, state, and then local. And most of them, the goal is to public safety. Say they don't care whether you are going to destroy your nutrient, they don't care your quality is bad, but they want to ensure people are not going to die by consuming your product. So public safety or food safety is the primary thing. The regulations set primarily for that. But from a food process perspective, they also want to protect the quality because you are buying from a product. If it's safe, that's good. But if the quality is not good, it's not formulated so that it tastes better and so on, the consumer is not going to go back to the same brand and buy the same brand. So you have to kind of consider that. You also have advances in science and technology happening. Like I think, as I mentioned, food science and technology is a multidisciplinary. You have automation, number of engineering innovations happening. You have some of the chemistry, nutrition innovations happening, and then innovations in microbiology, all kind of integrated to make the food technology much more excitement disciplines. And then the energy water utilization, wastewater reduction is also something that needs to be there. Now, when you develop a new product, oftentimes the expectation is that consumers, okay, I have a high pressure equipment which is expensive. I also have a water bottle, I can treat water bottle. So that's something not interested because consumer not going to find the value. On the other hand, when you look at guacamole or when you look at oysters and some other product, they provide unique benefits to the consumers. So the new technology, you have to be able to justify the value so that you can able to commercially sell and make sense of that. And so just doing because I have the equipment, it doesn't have a commercial value, it doesn't make sense. So you have to kind of pay attention to that. So this scale on the right is called technology ready scale. NASA, when they develop new technologies, they kind of use that. So for example, when the technology is in the lab level, this is called TRL1. When the technology is kind of ready for industrial application, TRL level 9. So a lot of the academic research is kind of done here, TRL1 to TRL3, whereas some of the pilot scale research, which can be done by industry as well as collaboration with academic, is done TRL4 to TRL6. So this is something neat. Why? Because the academia can do a lot of basic research, take the information to commercial, and then have the industry to manufacture at the large scale. But you need a collaboration between academic and industry. But oftentimes, whether it's in India or US, that is always have barriers. So a lot of times the food industry want to have all the intellectual property assigned to them so that they can able to securely produce the product, whereas the universities, they want to have that intellectual property. So that's one of the sticking point. And then academic, for example, we work primarily focus on educating students. So when you have a bachelor student, you have 4 years. When you have a PhD student, it may be 4 or 5 years and so on. So, it takes time. Whereas the industry, for them 3 months is a long term or 6 months is a long term. So, they have a different timeline to operate. So, if you kind of talk with each other, understand the barriers, then find a way to have a common ground, build a mutual trust, then you can able to have much more synergy of collaboration between academic and industry, so that you can get more products in the market. So, this is just a highlight some of the pilot plant facilities at Ohio State. We oftentimes invite the industry visitors to come and provide short courses and things like that, so that they understand the technology. Then they oftentimes do test up their product and then get into the commercial space and so on. We provide workshops, short courses, webinars, things like that. So, you have to find a way, wide range of means to reach the industry audience, so that they can able to work with you. So, future challenge, I think food processing, as I mentioned, it's a very dynamic. So, there's going to be more challenges. So, how do we feed healthy and nutritious foods for people? How do I reduce the environmental impact? Because a lot of times when you produce food, you cannot achieve zero impact. You're always going to have some waste. How do I reduce that waste? And food packaging waste is one of the major problems facing the world today. You probably heard the term microplastics. Microplastics everywhere, that can be a major problem. So, how do I develop biodegradable packaging material, so that can survive the process treatment, keep the product safe, but once in the landfill, it can degrade faster. Right now, it's more science fiction type thing, it's not reality yet, but I think maybe people in your generation become faculty members, industrial scientists, you may be doing some of those efforts. And climate change, like I think people say climate change is not real, but at the same time, we are seeing that radical climate change. You may have suddenly no rain, or you have a lot of rain. In any one of those cases, you may have a lot of losses with the crops and everything. So, food preservation becoming more important, because you kind of want to keep the processed food available, stored for longer times when you don't have a good crop yield or production. So, under those conditions, food processing even becoming more and more when you have more impact on climate change. So, in summary, food processing play a critical role in providing safe and nutritious food. It kind of virtually affect everyone in the planet one or other way, but I think we need to communicate better as a food scientists and engineers to common audience why food processing is important, because right now people just take them food processing taken for granted, but we need to kind of provide some education. And we use a lot of unit operations equipment to ensure safety and quality, and I think more and more emphasis is also going to preserve the nutrients. And food processing use a lot of energy, water, but we kind of want to reduce that. At the same time, we want to reduce the food waste, so that it can be much more economically, as well as minimal impact on the environment. So, this is just to give some reading materials on sustainable food processing. So, you may take a look at it if you are kind of interested in, and so it kind of provides some idea. And with that, I think I am going to stop here and have some time for questions.
Hello, Dr. Bala. I had a question regarding the reaction kinetics. I want to know how we can put the reaction kinetics to use when we are dealing with shelf life of food. how does that come into the picture, the mathematical model to determine shelf life of food, like when we are calculating it through accelerated shelf life studies?
Okay, sure. So we are going to talk about reaction kinetics in the next two lectures. This is going to be one on food safety, the second one on the what I call the quality kinetics, and then from there we can probably talk about how do you determine processing time based on the microbial resistance for different things, or the nutrients and enzymes and so on. Then we also talk about the storage studies. So I think basically, for example, you look at I think I'm briefly telling you, but there's extensive literature available. So let's look at one nutrient. You want to look at how that nutrient changes over storage. And normally, if the product is kept at 25 degrees Celsius, and it may have 3 years shelf life, but 3 years doing experiments in the lab is going to be difficult. So then you probably choose higher temperature, like for example 37 Celsius, and then see how that nutrient accelerated, deteriorated over a certain time. Then there are tables available converting that accelerated degradation to normal shelf life, thereby you can able to determine shelf life. And I think there are number of books published. So for example, Ted Labusa, he has done a lot of publications in the 1980s, 90s about shelf life extension.
Come again, what's the name?
Labusa. I think I have one reference in the next one of the presentations.
Hello, sir. Sir, my question is, recently in various publications, they are introducing sustainable development goal. So, in case of food science also, we are seeing the few journals, they are mostly highlight, if you can say sustainable food technology. There is a special paragraph we have to write, what is the sustainability point of view. From your, as a academic person, so what is the practical application of the sustainability? Is it how much it can be and practical life application? Though we are claiming in each paper, this is sustainable technology, that will be the novel technology, but in real scale, the ideal value, what we are performing in the lab scale, that is far different from this industrial scale. So as per your experience, can you, sir, give us any overview about the what we claim in the lab scale and how much is the industry we are getting, what is the difference percentage scenario?
Right. Yeah, I think the term sustainability is more like a buzzword. It's kind of, you have to use the term sometime to get maybe from a publication point of view or grant application point of view and so on. But I think the real understanding of sustainability and what is really needed to get the sustainable food processing is still evolving. And in fact, I think sometimes people may not even acknowledge food processing needs to be sustainable, because they think that it's probably sustainability is more from environmental or other means. Food processing is nothing to do with sustainability. But I think as I mentioned earlier, food industry is probably one of the high energy spending thing, and water. So you think about sustainability from the following way. How do I make a safe and nutritious food? At the same time, how do I reduce energy use and water use, right? And then waste reduction. So how do I accomplish that? Obviously, when you have a even novel technology, you're doing in 5 ml or 50 ml or 5 liter, it's not going to provide that sustainable thing. That metric become more valuable when you are mass producing, not only in India but maybe different parts of the world, so that it's more a real impact. Until then, some of these things are, think about this as a exercise to get you learn the principles, but may not have some real meaning at the moment.
I also wanted to know how the industry is dealing with stress adaptability, that various bacteria tend to show if they get exposed to sublethal stresses. So how does the industry deal with those kind of stresses, especially when they are dealing with disinfectants?
Right. Yeah, that's a great question. Now, the stress adaptation is probably something we may not have a full grasp of it, especially with a range of different methods. Let's take a simple thing, heat. We have been heat processing various foods probably now close to 100 years. If stress adaptation is something meaningful, now we should have had superbugs which are highly resistant to heat, but we don't see that, right? Like I think for those of you not microbiologists, stress adaptation is basically, let's say you can kill the bacteria at 70 Celsius. The concept here is that with repeatedly heating the food to 70 Celsius, the bacteria become gaining more resistant, so that it requires now 75 Celsius to kill it, and then eventually 100 Celsius and so on. So they are saying when you develop processing technologies, you are killing or you are developing super resistant bugs. So that's the concept behind stress adaptation. While this concept stress adaptation is probably there, and you can see microbial population, like we have 100 people, 100 people are not same, each has certain characteristics. So the same way when you have 100 microorganisms, different microorganisms have different resistance, so there's going to be some distribution of the resistant characteristics. But nevertheless, we have been pasteurizing food, for example, milk 72 Celsius 15 seconds, even though there are agencies monitoring that. I think we haven't changed that value over last several decades. So it's kind of same. So that means that stress adaptation is important, but not necessarily something we have to too much worried about, because there are times people said we are developing high pressure processing. Now we are going to have bacteria which are highly resistant to pressure. We are never going to get rid of that and those type of things. But these are all fear, but not necessarily practically relevant.
I would also like to extend the question and ask, how does this differ when we are dealing with biofilms? So wouldn't that be a bigger challenge?
Right. I think biofilms again, can be a challenge, but if you have proper sanitation methods developed, biofilms can be easily eradicated. So I think that way, like I think, mistake happens when you don't properly sanitize your equipment or operations. So that allows the development of biofilm over time. It's just the left, what I call, on the part of the processor, they are doing poor job that led to the biofilm. Then it's difficult to get rid of. But when you do regular sanitation, cleaning, all those things, we can avoid developing some of those issues.
Yeah. Thank you so much.
Thank you.